I'm Blake Edwards. You've seen me as such fine quality chemistry educational videos as Chemistry and History. Who would have thought? And fine quality chemicals don't just happen, you know. All right, we're going to continue on talking about acids and bases. In the last video, I gave you an introduction about Bronsted-Lowry acid and base, what was their definition, and the Arrhenius definition of acid and base. Okay, so now we've also talked about conjugate acids and conjugate bases. If you don't know what I'm talking about, you need to see the previous video. Okay, and then you go from there. Now, we also talked about the idea about water breaking up. We talked about the idea of water breaking up being H2O into H3O plus, and then the OH minus, the conjugate base and the conjugate acid as a result. And we understood that the concentration of the hydronium, the H3O plus and the hydroxide ions, that there's a certain scale that we have, and we use a pH scale, and it's logarithmic in nature. So we looked at the pH numbers here. So pH is the negative log of whatever the concentration of H3O is. Okay, now the thing is, you'd say, well, why the negative? Well, if you take the log of the concentration, you're going to get a negative number. That's the reality. Now, you can find out what the concentration of the OH is based off of the pOH. Well, wait a minute, how would you know the pOH? Well, the pOH, it's pH plus pOH equals 14. And that's a key thing, because remember, we're talking about the acid and the base, combine them together, and you essentially get the concentration of the acid and the base in plain old water, that 1 times 10 to the minus 7th molar, or pH 7. That's the idea behind it. Okay, so we're going to look, we talked about the idea of calculating the pH. So here is a concentration of HCl. We look at that, and it looks pretty decent. 0.035 molar HCl. Calculate the pOH and the concentration of the OH. Well, we can go ahead and find the pH first, because they gave us the concentration, which in this case, I think I may have made a typo. I put in the log of 0.25 as opposed to 0.035, but you get the idea. And we'll have a pH of 1.6. Ooh, that does have some concentration to it. Now, we can figure out the pOH because we can take the 14 minus the pH, because remember, pH and pOH together equal 14. And pOH is the opposite of the pH. So 14 minus our pH of 1.6 gets us 12.4. Ooh. All right, so now how do we go find the concentration of the OH? Well, we can take the inverse log of the negative concentration. What does that look like? Well, here we are, our concentration of OH is equal to 10 to the, what is our negative of the pH? The pOH, well, that's 12.4. We got that from here. Now we're making that a negative. Remember, we're taking the 10 to the negative concentration of the pOH, and that gives us 3.98 times 10 to the minus 13th molar, compared to what we originally had here. Well, remember, I made a slight mistake there. Okay, but if you look here, this is definitely more concentration of H3O ions than certainly we have the OH minus ions. So that would be a pretty careful thing. That would be an obvious thing. Okay, so over this table here, given the pieces of information you have, you would be able to fill in the information. So here we have a pH of 3.5. Well, we can take 14, take away 3.5, and that'll get us our pOH. Over here, we have a pOH of 18.4. We can subtract that from 14, and that will give us the pH. You'd say, okay, well, what about the concentrations? What about the concentrations themselves? Oh, that's not too bad. Remember, if you're going to go find the concentration of something, you're going to take the inverse log of the negative pH, or the negative pOH. Do refer to your formula, okay? And same thing with the H3O, if you want to find out the concentration. Now, that works great for strong acids and strong bases, but that's not going to work for weak acids and weak bases. You say, well, what do you mean? Well, remember, there are strong acids and weak acids and strong bases and weak bases, and the idea behind that, ladies and gentlemen, is how well do they dissociate in water? How do they dissolve? How do they break up in the water? So when we look at something that's weak acid, well, it's basically less than 5% of the acid actually dissolves in the water, as opposed to a strong acid, which it's 100% dissociation. It's great stuff. Okay? So weak acids, we have to use a different system. We have to use a different system in order to get our pH and our pOH and our concentrations, because it is less than 5% dissociation. So we are going to have to use the equilibrium system that we had, the ice table. Ice, ice, baby, ice, ice. Okay, I'll stop. So let's take a look here. So let's go ahead and let's work through an example. And remember, this idea also can apply to bases as well. So I have a 0.25 molar solution of HC2, H3O2. Okay, and they do give us the equilibrium constant, or the dissociation constant, and that happens to be 1.8 times 10 to the minus fifth. That's what they gave us. So, ooh, that's really, really, really tiny. Okay, well, that's great. So, wow, where do I even begin? Well, remember, when we're looking at something like this, we have to assume it is in water. Excuse me, it has to be in water. And we, instead of writing this out for the entire equation, we can turn around and say, okay, this is A. Because really the only thing we're interested in is what is up with our hydrogen. That's what we're looking at. So here we go. We're going to have our H with our A. Now that's going to be in an aqueous solution. Oops. AQ for aqueous plus, and I'm going to color code this one. Here's H2O, and we're assuming, yes, it's a liquid. We're also assuming that it's going to go back and forth, okay? That it's going to dissociate and reassociate and all that, okay? So we have that going. And, well, what do you end up having? Well, what you end up having is an A minus. Ooh, hey, what do we call that? Well, if this is an acid and it lost a proton, guess what? This becomes a conjugate base. Yes. And, ladies and gentlemen, we are going to have H3O plus. Oh my gosh, that's our conjugate base because it picked up a proton. It totally picked it up. That's the beautiful part. So notice I didn't have to sit there and write C2H3O2. Oh, that'd be so boring. So, and that's what the experts do. They do write it this way because they're not so much interested in this part of the acid necessarily. They're interested in what's happening with that proton. That's what they're interested in. Okay, so this is what we've got. Now, the beautiful part about doing the ice table, okay, as we move along here, we can go ahead and there's a few things that we can say. Well, okay, it's not, come on, right, thank you. Right, thank you. Right, thank you. Okay, so now let's take a look at this. For some reason now it's trying to, I have to change this. It's okay. I need my 100% back. Thank you. For some reason, it was switching to the entire page width. So you're seeing, it was seemed to be getting smaller and smaller. And it's like, okay, I need to have my people see this stuff. That is kind of important. All right. So what do we have? Well, remember we have our initial, we have our change, and we have an equilibrium. That's where we get the ice table. Ice, baby, ice. Yeah. Okay, vanilla ice I am not. However, when we look at the H2O liquid, does it play a part in this equilibrium? No, it doesn't. It's not really doing anything, it's just there. Okay, so guess what? Do I have to worry about the H2O? No, I don't. Now, what about this? Well, we have our initial concentration of 0.25 molar. That's what we have. Now, what can we say about this side here? If this is what we started out with, we have to assume there's nothing over here. And why? What is that telling us? The reaction hasn't started yet. We have all this reactant that's ready to break apart, fall apart, entropy, chaos. So that means this is going to be 0. That's going to be 0. Now, obviously, there's got to be some kind of a change going on here. Because if there isn't a change, then why are we doing this, right? So, in this case here, we know that there's got to be a minus x. Now, why am I saying a minus x here? Well, one, I don't know what kind of a change it is. I don't know what the equilibrium, because what we're trying to find out is what is our equilibrium concentration. And the other thing is, it's a negative x. Why? Because it's breaking down. It's falling apart. It's melting. It's decreasing. Okay, that's why the negative. Keep paying attention. The negative tells us the direction. It's falling apart. It's going. So what's going to happen over here is going to happen over here. Now, the fact is that this is 1 to 1 to 1. That means these guys are going to be both a plus x. If we had a 2 in front of that H3O plus, guess what? It would be a plus 2x. Yeah, exactly. So this is what we've got, ladies and gentlemen. All right, now, we're going to sit there and we're going to assume that x is very small. And you'd say, wait a minute, why would we assume that? Why can't we use the quadratic formula on this? Dudette. It's already less than 5% dissociated to start with. Why are we making this more complicated for ourselves? Okay, why? So, here we go. We got ourselves a 0.25 because we're assuming x is so tiny. We don't have to worry about it here. Okay, and then over here it's going to be x and x. So this is what our equilibrium concentration looks like. This is what we have. We don't know everything quite yet. So it's going to assume x is pretty small. So remember our acid, our dissociation constant there, that formula. Think about the equilibrium chapter. Here we go. Remember they gave us our Ka right here, 1.8 times 10 to the negative fifth. Okay. So 1.8 times 10 to the negative fifth is equal to, all right, don't you believe it, x squared, because remember we got these two because it's products over reactants, divided by 0.25. Oh yeah, we're so going there. Okay, so far so good, I'm hoping you guys are going with it. And again, I'm not as rushed when I go do something like this. So, basically, we solve for x, multiply both sides by 0.25, that cancels out. And then here, you'll have this multiplied by 0.25, then you take the square root of it, and you'll find out that x, ladies and gentlemen, x is going to equal, 2.12 times 10 to the negative 3. Okay, wonderful. So we know that this is going to be our 2.12 times 10 to the negative 3, 2.12 times 10 to the negative 3. Great, we got the equilibrium concentration. So what? Well, at this point, the so what, ladies and gentlemen, we can figure out the pH. The pH is equal to the negative log of our concentration, which is 2.12 times 10 to the minus 3. Wait, hold on. Where are you getting that number? Well, remember, going back up here on the ice table, we're looking at this equilibrium concentration because we're looking at the concentration of H3O ions for the pH. That's the key thing, ladies and gentlemen. We're looking at the concentration, the equilibrium concentration of the H3O. Am I worried about this one right now? No, not particularly. That's the one I want. That's the one I'm really interested in. Well, why do we have to go do the X here? Because you don't know what the results are going to be. That's why we still had to do this. No choice. You had to go through it. Okay, let's move on here. So we can take the pH, negative log of 2.12 times 10 to the minus 3, and oh my gosh, we have a pH equaling 2.67. Wow, I want that poured on my skin. Because man, that would be painful. Ooh, I would not want that. I really would not want that. Okay, we found the pH. Awesome sauce. What about pOH? Okay, pOH is going to be easy. Because remember, pH plus pOH is equal to 14. Yep, so 14 minus 2.67 is going to equal, oh, I think it was 11.33. That's our pOH. Okay? All right. Any questions on this part? Well, hopefully not. Okay? Now, can we go and figure out the rest of it? Yeah, we can. We can go figure out the concentrations. Let me check on my timing here. And yeah, I'm kind of running low on the time here. So let me show you guys. I can't calculate it out. I didn't have it pre-calculated on my paper this time around. But I'm going to show you what you do to make it easy. All right? To find the concentration of H3O plus, okay, listen carefully, you're going to take 10 to the, you're taking the inverse log, not the e to the inverse log, it's 10 to the, not the scientific notation, just 10 to the, okay, and you're going to take the negative of, oh goodness, the pH, which is negative 2.67. And that's going to give us our concentration of H3O plus. But hey, there's one more round, once more, okay? We're going to look at the concentration of the OH minus. But that's also equal to 10 to the negative 11.33. And that, ladies and gentlemen, will give us our concentration of our pOH. Now, here's one way you can take a look and see if things are working out. This OH should be a very, 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 very small number. Should be very tiny. Why? Because the concentration of the H3O should be a lot higher. It should be a bigger number than this. Well, wait, wouldn't they be equal to each other? No, and you know why they're not equal to each other? Because the pH is 2.67. If it was a pH of 7, then the pOH would also be a 7, and you would have the same amount of the H3O and the OH. Okay, guys, I gotta wrap this one up. I hope this will help you out, and until then, take it easy.